Here's our recap on 7.1 and our introduction into sampling distribution. So as you see on the screen, these were our outcomes for today that would really be able to distinguish between a parameter and a statistic. And if you weren't in class, what we did first was a drill where we cut out definitions and notation, and we really thought about the difference between all of these definitions and the notation. So you can read over all of this, you can pause the video and look at it, but what I wanted to emphasize is that your parameters are the big picture from your population. Right, so once you identify your population of interest, you think about the parameters. Maybe you're thinking about the population mean, population average. In that case, you would use the value of mu. Ignore that underline under this mu right here. Oh, but the problem is it's very hard to get parameters. It's not always the easiest to figure out what mu is. So what do? When we don't know the parameter, we take a sample and we calculate a statistic. Your sample mean is the average of your sample data. This is a snapshot of the bigger picture. And so then your sample mean gets the notation of X bar. Both of these are averages, but your mu is your population mean. Your X bar is your sample mean. Notation is really important here. You've got to know the difference. And then there's one other mean to talk about. And what this is if you take multiple samples of all the same size, okay, this word here is important, and you average all of those average. So if you average all the X bars from every possible sample size, or sample of size n, what you get is a sampling distribution. And the average of all the averages is the mean, the average of your sampling distribution. And we call it mu of X bar. Now, one of the questions lots of people ask in their reflections is, what does it mean to be an unbiased estimate of the population? If your mu of X bar, if this value right here, the mean of your sampling distribution, is equal to the mean of your population, then it's what's called an unbiased estimate of the population. If mu of X bar, the mean of your sampling distribution, is equal to the mean of the population, then it is an unbiased estimate of the population. We also have to know the difference of our notation with standard deviation. So again, we have our parameter, and that's the sigma. This sigma here is the standard deviation of the population. It is very difficult to have this value. So what do? We use a statistic. When we don't have our parameters, we use our statistics, and the sample standard deviation we label as S. It's the average variation from the mean of a sample of a certain size n. And then we have the standard deviation of the sampling distribution. So this, again, if you put together all possible samples from the same size, every single possible sample from a population, the average variation we call the sigma, the standard deviation of X bar, the standard deviation of all your samples. Notation is really important, and I'm going to be stressing it a lot over the next several months. So what's all this mean? Let's look at some population data that I gave us in class. This is the population of quarterly exam scores from a couple years ago on the quarter 2 exam of 100 AP Stat students. Okay, this is population data. So what I would be looking for if I was labeling this is I'd want to know the mean of the population and the standard deviation. If I had all this data in my calculator, I could run 1-bar stats. Right? This is 100 students, so obviously I can have the parameters. I can calculate this mean and the standard deviation, but let's, for the sake of understanding, pretend I cannot calculate this. The population's too big. Obviously 100 is not too big, but let's pretend it's too big. So what do? And this is what we did in class. What I had you do was, from that sample of 100 students, I had you take samples from the population. Here's the population up here. I had, oh, and I can't spell, population, I had you pull samples of size 5. And you each did that multiple times. Each time you took a sample of size 5, you calculated the average score from those 5, and you got an X bar value, which you see on what is known as our sampling distribution, which isn't complete because it's not all possible samples of size 5, but we're starting it. This is the start of a sampling distribution of quarterly scores for n equals 5. And you can see these averages range. We've got a low value here of, kind of hard to read. Let's say it's 67. I can't really read that. So a low value of 67, a maximum of 88. So our range here of our averages of size 5, remember this was 5, a sample size of 5, we have an average low of 67, an average high of 88, and if I'm estimating the actual average of the sampling distribution, I would say it's probably right about 75. It's just an estimate. But looking at the beginning of the sampling distribution, I would say the average is about 75. Now let's go back up to this image of the population. Look at the population data. I have a min of 50 and a max of 98. I have a lot more spread here. I have a lot more spread in my data, a lot more variation or variability here when I just have a sample size of 1. Population data is a sample size of 1. We're looking at one person at a time. When I increase my sample size, and this was a big takeaway, when I increase sample size, my variability or my spread, my range, my standard deviation, my variance, my variability will decrease. So when I increase my sample size, I went from a sample size of 1 to a sample size of 5, and that decreased my spread. I had a range of 50 to 98, and then it decreased from 67 to 88. And this is because we're looking at averages, not one individual at a time, but an average of 5 individuals. Now, going back to that unbiased estimate of the mean, if I was going to look at the average of the population, I did calculate it. The actual average of this population is, in fact, 75. Oops. Hold on. So my average here is 75 for the population. Remember what I said. We were working with an unbiased estimator of the population if the mean of the sampling distribution is in fact equal to the mean of the population, which they are in this instance. Okay, so just a reminder of these big ideas here that I just went over is that an unbiased estimator is a statistic is an unbiased estimator if the mean of the sampling distribution is equal to the true parameter, which we just saw in that previous example. And then a big takeaway about variability or spread. Variability is a fancy word for the spread of your distribution. Increasing sample size will decrease the variability of a statistic. We're going to build from here. Let me know if you have any questions.